In section 16.3, we're going to start with the autoionization of water. And for the autoionization of water, the whole point behind this is to start doing calculations with hydronium and hydroxide ion concentration. So let's start with autoionization. The word autoionization is, what that means is you have two of the same molecule, for example, water, and that one of them becomes a cation and one of them becomes an anion. Well, we will find that if you've got water, pure water at 25 degrees Celsius, you'll find that about 2 water molecules out of every 550 million of those water molecules, so 500 million water molecules, they will dissociate to give you hydronium and hydroxide. So it's not very many, but it is enough that it is something that is measurable. It is something that is measurable. Now, I will qualify this. I will qualify this and mention something about this, that temperature is important. The equilibrium constant expression for this is going to be concentration of hydronium times concentration of hydroxide. And the reason we don't have water is because water is the solvent, so we don't put that into the expression. Because this is a special kind of equilibrium constant, we give it a special subscript, W, and that is Kw is for, of course, water. We call that the ion product constant for water, and it's simply the dissociation constant for water. All right, it's 1.0 times 10 to the negative 14 at 25 degrees Celsius. This number changes pretty significantly if you change the temperature. For purposes of this class, we're going to stick with 25 degrees Celsius for all of our pH and acid concentration, base concentration, all those calculations. We're going to stick with 25 degrees Celsius. If you change the temperature, it's going to be pretty significantly different. Like by the time you get to 40, it's like 2 times 10 to the negative 14. I don't remember the number exactly, but it is pretty significantly different. Okay. We can use this formula. So hydronium times hydroxide is equal to 1.0 times 10 to the negative 14. We can calculate hydronium or hydroxide for pretty much anything. So like if we've got anything that's an aqueous solution with an acid or base in it, if we know one, we can get the other. So that's our formula, again, 25 degrees Celsius, and we can use it to calculate hydronium. We will find if the hydronium ion concentration is greater than the hydroxide, then the solution is acidic. If hydronium is equal to hydroxide, the solution is neutral, and in pure water, that is going to be the case. And if the concentration of hydronium is less than hydroxide, the solution is basic. So we're going to look at numbers 29 and 30, and we'll need the calculator on this, so make sure you get your calculator out. So number 29 and 30, let me move over there. I'm going to have to adjust my camera again. Okay. Oh, I didn't want the graph clear. All right. So it says here, calculate hydrogen ion. So calculate the hydrogen ion concentration for each of the following solutions and indicate whether the solution is acidic, basic, or neutral. So we want to use our equation for these. So Kw is equal to hydronium times hydroxide, which is equal to 1.0 times 10 to the negative 14. So if we're looking for hydronium, and it says here H plus, but remember H plus means hydronium. So H plus and hydronium are the same thing. So if we solve this for hydronium, then we're going to get hydronium is equal to Kw over hydroxide, which is 1.0 times 10 to the negative 14 divided by that number. So 0.00045. And so we want to put that number in. So 1 times 10 to the negative 14. And you want to make sure that you're using your calculator correctly here, which is why I have it right here while we're doing this. And then we're going to divide that. So 1 times 10 to the negative 14, and then 0.00045. So we're dividing by 0.00045. It is important to put in the correct number of zeros. Otherwise, you'll end up with the wrong answer. And you'll see we get 2.2222 times 10 to the negative 11. We're going to round that to 2 sig figs. So we're going to call that 2.2 times 10 to the negative 11 molar. All right, our concentration of hydroxide was 4.5 times 10 to the negative 4. And for hydronium, it was this. Hydroxide, in this case, was greater than hydronium. And that means that it was basic. All right. So probably a good idea. Go ahead and attempt to do these two, like stop the video and attempt to do these two. All right. So I'm assuming you stopped the video and you attempted to do these. So hydronium, 1.0 times 10 to the negative 14 divided by 8.8 times 10 to the negative 9. So we'll do 1 times 10 to the negative 14, and we will divide that by 8.8 times 10 to the negative 9. And you'll see we get 1.136. We're going to call that 1.1 times 10 to the negative 6 molar. So now we want to compare. Hydroxide is 10 to the negative 9 here, and hydronium is 10 to the negative 6. 10 to the negative 6 is bigger than the 10 to the negative 9. So hydronium is greater than hydroxide. So therefore it is acidic. Let's try that again. Acidic. That is acidic. All right. So now, in which hydroxide is 100 times greater than hydronium. Well, hydroxide is greater than hydronium. This is basic. We already know up front that it is a basic solution. When it says hydroxide is 100 times greater than hydronium, then we know this already. Hydroxide is equal to 100 times hydronium. And since we're looking for hydronium, we're going to put in place of hydroxide, we're going to put 100 times hydronium. So our equation 1.0 times 10 to the negative 14 is equal to hydronium times hydroxide. And as I mentioned, in place of hydroxide, we're going to put 100 times hydronium. So 1.0 times 10 to the negative 14 is hydronium times 100 times hydronium. So 1.0 times 10 to the negative 14 is equal to 100 times hydronium squared. Okay, so there is hydronium squared, and I'm going to fix that real quick because that looked ugly. So hydronium squared is equal to 1.0 times 10 to the negative 14 over 100. And that means hydronium squared is, and I know what this is going to be. That's going to be 10 to the negative 16, but I'm going to go ahead and put it in. So 1 times 10 to the negative 14 divided by 100, and that's going to give us 1 times 10 to the negative 16. So 1.0 times 10 to the negative 16. And then we'll take the square root. And so hydronium is going to be the square root of that number. And the square root of that number, we will do second square root, second answer, and we get 1.0 times 10 to the negative 8 molar. All right, so that will be our concentration of hydronium. Next, we in number 30, we want to do the same thing, but on number 30, we're going to be calculating hydroxide instead of hydronium. So we will be calculating hydroxide instead of hydronium. All right, so same equation, Kw is equal to hydronium times hydroxide, which is equal to 1.0 times 10 to the negative 14. All right, and here we're solving for hydroxide. So hydroxide is equal to Kw over hydronium. And just as a reminder, hydronium and H plus are the same thing. So 1.0 times 10 to the negative 14 divided by 0.0075 molar. And then we'll get 1 times 10 to the negative 14 divided by 0.0075. So again, 2 sig figs, we have 1.3 times 10 to the negative 12 molar. The 1.3, that's for hydroxide, so 10 to the negative 12. Hydronium is 10 to the negative 3. That means the hydronium is greater than hydroxide ion concentration, and so this is acidic. It is an acidic solution. All right, let's do the next one. Hydroxide is equal to 1.0 times 10 to the negative 14 over 6.5 times 10 to the negative 10. All right, and so 6.5 times 10 to the negative 10, we'll put that number in. So 1 second, negative 14 divided by 6.5 times 10 to the negative 10. And we get 1.5 times 10 to the negative 5. So our concentration of hydronium was 10 to the negative 10. Hydroxide is 10 to the negative 5. That means hydroxide is greater than hydronium. And so this one is basic. On this last one, it says a solution in which hydrogen or hydronium is 10 times greater than hydroxide. So if hydrogen is 10 times greater than hydroxide, we already know that this one is acidic. So on part C, it is acidic. All right, well, if hydronium is equal to 10 times the hydroxide, and we know that 1.0 times 10 to the negative 14 is equal to hydronium times hydroxide, and we're looking for hydroxide. So we want to replace the hydronium with 10 times hydroxide. So we're going to have 1.0 times 10 to the negative 14 is equal to 10 times hydroxide times hydroxide. So again, in place of hydronium, we put 10 times hydroxide. Well, that's going to give us 1.0 times 10 to the negative 14 is equal to 10 times hydroxide ion squared. Well, if we divide both sides by 10, we'll get hydroxide ion squared is 1.0 times 10 to the negative 14 divided by 10. I know that's going to be 1.0 times 10 to the negative 15, but let's go ahead and put that in our calculator. So 1 times 10 to the negative 14, and we want to divide that by 10, and you'll see we'll get 10 to the negative 15. So 1.0 times 10 to the negative 15 is hydroxide squared. So hydroxide is going to be the square root of that number. So we'll do second square root and then second answer so that we don't have to type it in again. Close parentheses, and we'll get 3.2. Not 2.3. My brain did this backwards. So 3.2 times 10 to the negative 8 molar. So 3.2 times 10 to the negative 8 molar. And all right, so that is our hydroxide, and that was the goal there. We already determined that that one was acidic. And so there we go. That one is our solution for that. Okay, so I'm going to go back over here. And the next topic is looking at the pH scale. Our definition for pH is it's the negative logarithm of the hydronium ion concentration. So if you know the hydronium ion concentration, you just take the negative of the logarithm and you will get the pH. All right, and for this one, I am going to set this up as a special screen here so that you can see as a split screen, so you can see the calculations that we're going to do, and you can see the presentation as we go along. And that way we can do the calculations and punch them into the calculator as we go. So normally if I were in a class, I would have my students just do these, but since we're doing this asynchronous, we'll do it this way. So 1.0 times 10 to the negative 7. So to take the negative log of that, you'll put negative log. Make sure you choose log base 10 and not natural log. If you choose natural log, you're going to get a very different answer, and we don't want that. So the negative log of 1.0 times 10 to the negative 7. Now, I put down a little thing down here, and it says sig figs, and I want to mention about significant figures. This number right here clearly has 2 significant figures. So that number has 2 significant figures. Well, that means that our pH is going to have 2 numbers after the decimal point. So here, when I enter that in, you'll see we get the number 7, but we want to record that as 7.00. Again, there's 2 significant figures. Only the numbers after the decimal point are significant in the pH. This 7 tells us the order of magnitude. And to illustrate that, so here we've got 1.0 times 10 to the negative 7. Well, let's do 1.0 times 10 to the negative 8. So again, negative log of 1.0 times 10 to the negative 8. We enter that in, we'll get 8, so that's going to be 8.00. All right, you can probably guess this one. All right, so you can go ahead and guess that one, but all right, so 1.0 second EE negative 5. And if you guessed 5, give yourself a prize. So again, it tells you the order of magnitude. So the number before the decimal point tells you the order of magnitude. How about this? So a lot of times I will do this one in class and I'll say, okay, does anybody know? Because like at this point, they're like, they can guess the number without actually using the calculator. And then they'll guess like 10 or something. And that is completely wrong. Oh my goodness, I hit my camera there. That's completely wrong. And so the best answer is just calculate it until you get a good feel for it. So 2.0 second EE negative 5. And you will see that instead of doubling the number, it's going to shift it by 0.30. So the number we're going to get there is 4.699. We're going to call that 4.70. So here we'll get 4.70. If we were to double it again, we get 4.40. Here, I'm going to do that one real quick. We'll do negative log second. So 4.0 and then second EE negative 5. And so here, every time we double it, the pH is going to go down by 0.3. So we double the concentration, pH goes down by 0.3. So there we go. And you'll see it comes out to 4.40. All right. So 2.0 times 10 to the negative 8. Well, if 1.0 times 10 to the negative 8 was 8, then 2.0 should be 7.70. Should go down by 0.2. But again, let's prove that to our negative log of 2.0 second EE negative 8. And we should get 7.70. And there it is, 7.70. All right, to show you that this second number affects the second number after the decimal point, we're going to do this. So negative log of 2.1 second EE negative 8. And we'll get 7.68. And then we're going to do the same thing. So negative log 2.2 second EE negative 8. Sure, I punched that in correctly, and I think it's 7.66. Yeah, 7.66. So there is 7.66. All right, one more. We'll do 5.0 times 10 to the negative 8. It's going to be somewhere in the 7s. Less, I should be 7.30, but let's go ahead and do it. So negative log 5.0 second EE negative 8. And we'll get 7.30. There it is. Oh, look, I have one more. This one should be 11.30. But again, let's do the calculation. I keep doing that. Say 5. So 5.0 second EE negative 12. And close the parentheses. And we'll get, I think 11.30. Yes, 11.30. All right, the whole point of this was to illustrate that the number over here gives you approximately where this number is. Like there at 7, if this number is bigger than 1, it's going to go down from there. So the bigger the number, the more it goes down. The number over here affects after the decimal point. Okay, so that is how we calculate. pH. I am going to go back full screen here. And we're going to do pH of water at 25 degrees Celsius. So here, Kw is this. We can use an ice table to calculate hydronium or hydroxide. So here is our dissociation. And here is an ice table. Now, since water is not in the expression, we're not going to put any values for the initial change in equilibrium for water. The initial concentration for hydronium and hydroxide are going to be 0 here. Since the coefficient for both hydronium and hydroxide is 1, then the coefficient for X is going to be 1. And so 0 plus X is X, 0 plus X is X. We're going to put those values in the at equilibrium into the expression. So Kw is equal to this, 1.0 times 10 to the negative 14, which is equal to X squared. So this is equal to X squared. We'll take the square root of 1.0 times 10 to the negative 14, and we will get 1.7 times 10, or 1.0 times 10 to the negative 7. I misspoke there. So X is equal to that. And so X is equal to hydronium, and X is equal to hydroxide. If you were to further, if you were to take the negative log of this, we already did this one a minute ago. If you take the negative log of that, you will get the pH, and the pH will come out to 7.0. So you want to get good at calculating pH, and we're going to do lots and lots of examples here in just a few minutes. Now, there are some other P scales, and one of them is important that we're going to use here in just a minute. P just means take the negative log of it. You can do pH, take the negative log of hydrogen ion, POH, take the negative log of hydroxide, pKw is take the negative log of Kw, pKa is take the negative log of Ka, my sandwich is take the negative log of my sandwich. We don't normally do that, but you get the idea. So P function just means take the negative log of it. All right, now there is a relationship between pH and POH. So here we've got the equation for the ion product constant and the expression for water. If we take the negative log of the equation, we'll take the negative log of this. Since it's a product, we can take the negative log of hydronium plus the negative log of hydroxide, and we'll get that. We'll have the negative log of Kw, which is pKw, and then the negative log of 1.0 times 10 to the negative 14, and that gives us 14. That gives us 14. So, like I said, this is pKw, this is pH, and this is POH. So that gives us pH plus POH is equal to pKw, and pKw is equal to 14. Now, caution, warning, this only works at 25 degrees Celsius. If we're doing a different temperature, pKw is not equal to 14. Just let you know that, and that could be something that fools people. Again, for this class, we're going to assume it's always 25 degrees Celsius. But once I release you into the wild, into the real world, you may find something else happens. So, all right. So the pH scale is right here. So here we've got pH and POH. You'll see that they always add up to 14. It is certainly possible that you can have pHs that are actually negative, and you can have pHs that are greater than 14. It's a common misconception that it's always between 0 and 14. It can actually go negative, and it can actually go greater than 14. Doesn't get too much further than that. And then these are just some common substances, and usually in class I'll talk about it. Sour things are usually acidic, and then bitter things are usually basic. And so this is just a few common things. All right, we're going to look at number 37. Number 37 is a little bit of a long problem, and so after number 37, we're going to stop this video, and we will have the next section. So, oh yeah, all right, yeah, we'll talk about those things right after number 37, and then we'll have the next video. So, okay, so let's go back to our in-class assignment. I'm gonna move this over. So typically when I do these problems, the way I like to do it is I like to do like one right after another. And so there's a logical way to go through this. You can use these formulas to get you from one of these to the other of these. And a couple of a couple of useful formulas. So I'm going to go ahead and write them down here. So Kw, which is 1.0 times 10 to the negative 14, is equal to hydronium times hydroxide. We know that one. And we also know that pH plus POH is equal to 14.00. So we know that. There's also one more thing. If we take our thing for logarithm, so our pH. pH is the negative log of hydronium. But if you want to solve for hydronium, then you multiply both sides by -1 and then take the anti-log and you'll get this. So hydronium is 10 to the negative pH. All right, POH is the negative log of hydroxide. And so hydroxide is 10 to the negative POH. So I will show you how it is that I punch these numbers in. So 7.5 times 10 to the negative 3. All right, so to get, you can do this one next, or you can just do pH. I'm going to do pH, so I'll do negative log of 7.5 times 10 to the negative 3, and we get this. So I will put that number in there, which is 2.12. All right, I'm going to do 14 minus the answer. All right, and that gives us 11.875. We're going to call that 11.88. Once we know the pH, we can determine if it's acidic or basic. If the pH is below 7, it's acidic. If the pH is above 7, it is basic. So this one is acidic. All right, now I'm just going to take that 11.875. I'm just going to do 10 raised to the negative of our answer. And that will give us our hydroxide ion concentration. So 1.3 times 10 to the negative 12. Again, the equation that I was using there is 10 to the negative POH. I just took what was in the calculator, and that gives me 1.3 times 10 to the negative 12. All right, so now I'm going to do these calculations. I'm going to turn off my microphone and just go through and do the calculations so that you don't have to listen to me drone on. All right. Well, I know that wasn't very exciting, but it was better than me droning on during that whole thing. So hopefully you were able to follow along with that, and hopefully I didn't make any mistakes while I was doing it. Okay, so let's go back to the video. I want to show, or back to the presentation, and I want to show you the I want to show you how it is that we measure pH. And there's a couple of things that we can do to measure pH. Here we've got some vinegar. Vinegar is about 5% acetic acid, and you can make accurate measurements using the pH meter, which and with a pH meter, it looks for the voltage across a circuit. So you put a cathode and an anode into the solution, and it measures the potential, and then it maps that potential, that voltage to a pH. So it's a pretty cool piece of equipment, and you know, one like this usually costs several $100s for one that is of this variety. So they've come down in price and are pretty easy, but still, one like that probably $200 or $300. If instead you don't want an accurate measurement of pH, you want an approximate pH, maybe to the nearest pH unit, or maybe you just want to know if something is acidic or basic. Well, you can use litmus paper, and litmus paper will tell you if something is acidic or basic. If you have red litmus paper, it will turn it blue if the pH goes above 8. So if you have a pH greater than 8 in the basic region, it will turn blue. And blue litmus paper will turn red, or it'll actually turn kind of pink if the pH is below 5. So we have neutral litmus paper that's become popular, and what you do is you just take a piece of the neutral litmus paper, put a drop of your solution on it, and it turns kind of a pink color if it's acidic, and it'll turn blue if it is basic. There are also indicators, and there are a whole bunch of different indicators. One that you probably used in the first semester was phenolphthalein. Phenolphthalein, if you've got phenolphthalein, if it's below a pH of about 8, it's completely colorless. If you got a pH of right about 9, it starts to turn a little bit pink. And if you get a pH that's greater than 9, like to 10, it's a dark pink color. Usually when we're doing a titration, we like to get it right on that edge where it just barely turns pink. And so here I've got a picture. Here's phenolphthalein. So 2, 4, 5, 7, all of those are colorless. You'll see right there at a pH of 9, it's just almost perfect, a light pink color. That's like the perfect pink color when you're doing a titration. And then if it turns this really, really dark pink color, that means you've gone too far, and that's at pH 10. When you're doing a titration, the difference between this and this is like half a drop. So if you've ever been stressed while doing a titration. These other ones, it's just showing you where the color change occurs. So for example, bromothymol blue, which we have here, anything below 6 is going to be yellow. So here you'll see 2, 4, 5, those are all yellow. Even at 6, it's still yellow. If you get right at 7, it's kind of a green color, and anything that's like 8 and above is going to be blue. And so that is pretty handy if you've got something and you want to distinguish, is it acidic or basic? And if it's acidic, it's going to be yellow, and if it's basic, it's going to be blue, and if it's right close to the pH neutral, it's going to be kind of a green color. So that one's really handy. Methyl red is another popular one. Its switching point is right about 5. You'll see here it's orange when it's at 5. Anything less than that, it's red. Anything more than that, it is yellow. You'll see even it's a little bit of orange there, even at 7, but that's methyl red. And just by changing the molecules a little bit, they can make it so that these numbers shift around a little bit. Thymol blue is really cool, and I don't have a picture for thymol blue, but below 2, it's red. Between about 2.5 all the way up to 8, it's yellow. At about 9, it's green. And then anything above 9, it's blue. That one's really cool. So you can also use a couple of these together to figure out what the pH of a solution is. So for example, if you had a solution that was yellow for methyl orange and red for methyl red, then that's going to be a pretty narrow region. It's going to be pretty close to 5. So it's going to be pretty close to 5. And of course, you can use sort of these in-between colors to get a good idea of the pH as well. So it doesn't give you exact pH, but this is a very powerful tool. And if you don't need perfect pH, then you can use indicators. People who do pool maintenance and try to get the pH of a pool just right, they use color indicators rather than use a pH meter. Although I think pH meters have gotten so cheap that now you can use pH meters on, you can buy a pH meter for your regular pool. But it used to be they just used indicators, and that worked fine. Okay, our next topic is actually in the next section, section 16.5. We're going to put that into the next video. So that's the end of this video.